Okay, so our next speaker in this session will be talking specifically about future hadron colliders. We'll have Michele telling us about the highest energy hadron colliders we can imagine.
Okay, so very good. Thanks for the invitation. I have this is difficult task to talk about all these topics in a little less than an hour. So of course I had to select a little bit, and of course the more we go towards the end of the talk, the more speculative all the statements I will make will be, because these are just the result of thoughts of the last couple of days without much discussion with the experts anyway. So I already put this as a disclaimer. The first part of the talk will be more traditional. Probably you've heard some of it already. I will just go through the, type of physics one does with a Future Hadron Collider. What are the detectors that one can build that satisfy the physics requirement, and highlight a little bit what are the challenges that were discussed already by the previous speaker a little bit in the discussion session. So just a trivial introduction on high energy hadron machines. So why we like high energy hadron machines, or hadron machines in general? Because if you're agnostic about what new physics is, or where new interactions will be, you are probing a relatively democratically distributed initial state, because you're producing quarks, gluons of different flavors. You're probing both the electroweak and the strong force at the same time. You can reach high center of mass energy because you have small synchrotron power loss, because of course, as opposed to a lepton collider, this thing scales like a 4 power of the mass of the particle. Of course, as you will see, this also comes with caveat at some point, and you can reach very high luminosity up to high energy. Of course, the cons are that you have large QCD backgrounds because the strong interaction is strong, as opposed to lepton machines. You get a lot of digets, TT bar, and also pileup is QCD interaction. So you get, because the cross-section of PP in elastic collisions is large, you get a lot of those simultaneously when you collide beams of protons. As I will argue, discovery machines for high energy, for heavy new states, these are, and but this is also suited to precision because you produce standard model particles with very large rates. You have many variants of proposed future high energy machines. Of course, the most popular is the FCCHH, which is a 90 kilometer ring in the CERN area with the highest possible dipole magnets of 16 Tesla or around that region. In the past, also other options have been proposed. The high energy LHC, where you put high fit magnets inside the LHC. This would get you to around 27 TeV, or you can also think about a cheap FCC with very cheap magnets, but a very large tunnel. This would get you around 40 TeV energy. The cost of FCCHH, which is a machine, as I will argue, is very costly. Of course, the main challenge, I don't know if you heard about this in the last days, you probably know this, is of course the magnets. The new baseline for the FCCHH magnets is 14 Tesla. This would get you to 84 TeV energy. You need a new superconductor to reach these higher fields. You need wider coils to maintain the overall current density. This means that you have 2 times the conductors you have in terms of volume, and therefore in terms of cost, than the niobium titanium magnets you have at the LHC. If you just do the maths, this is 4,000 magnets, so it's 10 billion just for magnets to fill the FCCHH. Okay, so that's already minimum cost. Then you add the infrastructure, the accelerator, the detectors, and then you get easily to 25 billion cost. Just a simple scaling rule for understanding a little bit what is the reach for high energy hadron machines. The number of particles, of course, that you produce for a given process is given by the partonic cross-section times the luminosity, and the partonic cross-section is the partonic's luminosity times the cross-section is the partonic luminosity times the cross-section, and you can just compute the partonic luminosity, and this gives you a range of access. And if you just do the scaling properly, you realize what you think intuitively is that if you get a factor 7 in the center of mass energy, you get a factor 7 in energy reach, provided that you can saturate with the proper luminosity, okay? So the smaller the mass, the larger time it takes to saturate the luminosity, but it is the way these things scale. In terms of standard model processes, what is interesting is, or any process for that matter, is that the cross-section between the two energy scales like the parton luminosity. So for low energy states, for example, Higgs, the Higgs production rate grows by a factor order 10 between 14 and 100 TeV. The higher the Q square of the process, the larger the boost you get in cross-section. This is what you see in this plot over here. And this is intuitive if you go to something which is beyond the kinematic reach of the LHC, so something like 10 TeV. Of course, then the boost is infinite because you have zero cross-section in one side and the infinite and a finite cross-section on the other side. So if you look at, for example, the production of Higgses with a PT of greater than 1 TeV, so this is a Higgs recoiling against a jet with 1 TeV, the cross-section for this process is a factor 400 at 100 TeV compared to 14 TeV. This is important because this will give you access to very clean Higgs produces 100 TeV, which you don't have access to at the LHC, or you barely have access to at the LHC, okay? And this has implications. This is just the same thing said differently, where you have all the processes at the as a function, all the cross section as a function of center of mass energy. The total PP cross section increases very little. So this is what I was saying before, is a factor 2 only, so very low Q square. If you go to high Q square process like TT Higgs or di Higgs, this increases by very large factors from 14 to 100 TeV. This is relevant also because the levels of pileups will scale like the total inelastic PP collision rate for the same instantaneous luminosity. And of course, if you put more current in, you will have a larger boost in instantaneous luminosity. But this means basically that if you were to collide the same types of bunches at different energy, the levels of pileup and the contamination of pileup won't be that different. Now, of course, you would like to aim for a 100 TeV machine to operate at a larger luminosity than you do at the Illumia HC, at least by a factor 5, and this is where you will get most of the increase in pileup, not from the PP collision rate, okay? Or at least that's where the big of the boost comes from. Standard model physics. Of course, such a machine is not only a discovery machine, but it's also, you know, again, the rates are very large. I told you the increasing cross sections for Higgs physics is a factor 10. You can consider another factor 5 or 10 from the integrated luminosity. So therefore, you would get a factor 100 more Higgses that you get with respect to Illumia HC. So this is substantial. You would like to benefit from all of these. However, standard model physics will be more forward. This is because, of course, the imbalance allowed by the PDFs is larger for a given mass scale, because the x's you're going to probe are going to be a smaller x. The kinematic range is larger. So, for example, if you look at how a VBF Higgs is produced at 100 TeV compared to 13, it will be produced more forward. So you need if you want to tag a VBF jet at the LHC, it's eta 3. At the FCCHH, it's eta 4. So you need more coverage, okay? Well, this is the same thing said differently. Of course, more coverage also buys you more hermeticity for things like missing energy and things like this. So in principle, you would like to do this not only for covering Higgs physics. Now, at the other extreme part of the range, if you look at multi-TeV energies, okay, you have a 100 TeV collider now, so you would like ideally to see Z primes of 40, 50 TeV at least. Therefore, you want to reconstruct particles with energies at the level of 20 TeV, okay? Because these are going to decay into typically 2 particles at least. At least this is the upper limit. So you want to be able to see this. You don't need necessarily very high precision for those kind of 20 TeV particles, but you need to at least see that they are there. So let's say if you put a target of precision for the tracking at 10 TeV, or a precision for a muon at 20 TeV, this is good enough to measure a Z prime to mu mu, for example, because there the levels of backgrounds from Drelian are very small. You just need to see the resonance, okay? And the tracking resolution scales like 1 over BL square. So in principle, if you want to maintain the same sensitivity you have at the LHC for a tracking system, you have 7 times more energy. You have You can do it several ways. You improve your single point resolution by a factor 7, you improve your magnetic field by a factor 7, or you increase your tracking volume by square root of 7, okay? Or a combination of these three factors, okay? Something obvious. And it turns out that simply by extrapolating current technology, this is very simple to do. As you will see later, it's not a big deal to obtain this kind of resolutions with current technology, because simply, tracking devices with 10 micro resolution, single point resolution are easily accessible at that time. And so this will be easy to do. For calorimetry, things go easily your way because, the containment of a shower scales logarithmically with the energy. And this is good for us because it means that if I increase by a factor 10 the energy, I just need one more interaction length in my calorimeter to contain my hadronic shower. And so this is what you see in this plot over here, where you see how many interaction lengths you need to contain 98% of a jet of a given energy. And you see that basically this buys you, if you're at the level of 11 interaction lengths for the full EM plus hadronic calorimeter, you can contain up to 20 TeV jets quite easily. And this is, just a 10% or 20% thicker calorimeter than you typically have in CMS or Atlas. It's not a big deal, okay? Now, where things get more complicated is for boosted topologies, as we discussed in the previous Q&A. If you think about a Higgs or a W or a top with 10 TeV energy, the full decay products will be contained to a angular of 0.05. Just for reference, this is smaller, or at least this is the same order of a single Ecal crystal in CMS. So this is 2 centimeters at 1.5 meter radius. So it would be very hard at these kind of energies to resolve any type of substructure with pure calorimetry, okay? Because all the decay products will just go within a single radius, a single cell, and you won't be able to disentangle particles coming from the different prongs of these topologies. Of course, the B field will help a little bit for charged particles because it will open up the jet a little bit. But since, as you will see, we foresee to have similar fields as we have in CMS or Atlas, this won't help that much. Of course, having a larger tracker would help a little bit also because it opens a bit. But at the end of the day, for this kind of energy and above, you will rely mostly on tracking to do substructure, okay? The calorimeter will be just there to help you to measure the total energy of the jet, but it won't give you any handle on the actual substructure. Tracking is well within the requirements for a 10 TeV energy. Typical tracking system will provide 10 to the minus 3 angular separation, so this is probably fine. But we will see a loss of performance compared to a 1 TeV top or a 1 TeV W or Higgs at the LHC. And there is not much way out unless we really go 10 times further away, okay? Which we cannot afford because we don't want a 10 billion type detector, okay? High PT flavor tagging also will, in some sense, suffer because if you take a 5 TeV, so B at rest has a 500 micron lifetime. So a 5 TeV will decay 50 centimeters within the tracker, okay? So it means that basically it will be decaying, of course, well away from your vertex detector. So you need in principle highly segmented tracking system to play the role of your vertex detector, and maybe you can exploit some techniques such as this is like a jet within a tracker, or you can see like from the point where it decayed to the point after, you can see a multiplicity jump. So first, if a 5 TeV charge B hadron will produce a track for the first 50 centimeters. So this is not something we're used to see. So the first, it will just behave like a sigma, a charge sigma or something like this, or omega minus or whatever, right? And then it will decay to something else, and you will see it this way. And you will probably reconstruct the invariant mass of these systems. But this, requires some thinking in terms of, algorithmic reconstruction of finite states to change the paradigm with respect to what we do now. Again, color singlets at very high energy substructure that we were discussing before. So it's very different if you compare a jet, a gluon of 30 TeV compared to a W. W is not charged with color, so it basically behaves like a tau, okay? So, and then if you can try to resolve the substructure over here, but otherwise it's basically a very, very collimated type of particles with very little radiation around, with the only things which it radiates are photons. If it's a W, if it's a Z, it doesn't even do that, or Higgs. You can have weak showers, but this is something we can discuss later. But this is something you can exploit, right? So you would do a W identification at these energies as you do tau ID, for example, at DHC. Same ideas. I won't discuss further. Interesting things, for people doing QCD, you will see the dead cone effect for passive particles. You would see tops radiating in a ring around itself because radiation is suppressed at small angles due to the fact that the top is massive, and this you will see also for QED radiation. And this is actually a handle you can use for doing top identification also, because the size of this ring is related to the mass of the top, okay? Same techniques here, I won't discuss as much. Yes. A singlet. Yeah, I mean, in principle, yes, because if you don't, the only way you can distinguish a W from a, well, W maybe not, because W is charged, so you might imagine you can see some photons and so on. Let's say Z from a Higgs, the only handle you have is to reconstruct the invariant mass of the jet, provided that you have enough resolution to reconstruct at least the prongs from the tracks within. So this is just a simplified image of what you would see in the calorimeter, right? Then you have the tracking information on top that can help you here. So, but it will have an impact, because of course you lose all the neutral energy. You have a 30 TeV jet, but you cannot resolve a 90 GeV mass over 30 TeV energy, right? So this is going to be purely given by tracking. But you know, it seems that tracking can do partly at least the job. Yes. Okay, well, the challenges for the detectors, I think Lorenzo he discussed a little bit earlier. I will not technology, but just to summarize what I said, you know, the LHC and the FCTHH. So you want to still do the same kind of physics you do at the LHC, right? So all the standard model physics, maybe B physics is arguable because, or flavor physics. I don't know if there will be a dedicated flavor detector for the FCCHH. That we can discuss this maybe in the Q&A, but at least the bread and butter standard model physics, WZ, Higgs, and so on, you will want to do at the FCCHH, but you want to also probe a higher mass regime. So the same challenges you have here, but on top of that, you have the boosts there. Here, the challenges are much more because you have higher rates, larger backgrounds, physics is more, as I said. But what you can do, as I will argue later, is that a little bit of the rate that you have here to go to higher PT, where things are going to be much cleaner, and arguably they can provide the same sensitivity or better sensitivity than you have at the LHC. This is typically the so earlier, just the key numbers here. The fluence. So this is the amount of radiation you get at the end of the lifetime is, okay, I think you showed 20, I think it's more like 50 times the Illumina HC, depending on how many detectors, or how many, what is the luminosity one assumes. So this is really challenging. Peak luminosity is 6 times larger than the Illumina HC. There will be also a two energy phases. And here you can see a bunch of numbers which tell you, for example, how things scale, such as, you know, how much energy you deposit in the calorimeter, was the typical distance while up interaction, because the bunch crossing and the bunch length would be similar, but you pack in more interaction. So you have a stranger more. So this is the baseline detector that could do the job. You can think of it as an Atlas type of detector with two LHCBs in the end caps. I say two LHCB because if you want to cover up to eta equal 8, you still need a forward spectrometer that gets you there, because here you are limited by the beam pipe. You cannot go below eta 4 because this is the closest you can put your vertex, so you need to extend in the forward region, okay? Then, okay, you can argue whether you want a dipole here or a solenoid. We prefer solenoids because it gives you phi rotational invariance, but still, this is the kind of detector. I'm not sure this will be the detector that will be built. Probably some compromises will be done, but this is a detector that could get you at least halfway there. As I said, the data rate is 10 times larger than Illumina HC. The radiation environment is 50 times larger. And I will just go quickly through. This is the type of tracking system you can design. Add central tracking and forward spectrum. 3 times better single point resolution than we have currently at high lumen HC. This is doable. It just increases a lot the number of channels. So you have to understand how you can get all this data out without affecting the capability of your tracking system. But in principle, it's doable. It's just money. Okay. Just quote unquote, man, and power and so on. Yeah. Yeah, of course. Yeah. Yeah, although you don't need to read them all at the same time, right? Especially in the more forward part, in the external layers. Okay, calorimetry. Okay, Atlas has solved this. We have liquid calorimetry is easy. It's radiation hard by default. You can build a liquid argon ecal. You know how to do it. HCal. It's a borrowed concept also from the Atlas calorimeter with scintillating tiles. The magnet is a very complex system with this central magnet and these 2 forward magnets. Muon spectrometers, it appears as I will argue, 2 stations separated by 1 or 2 meters with a 50 microposition resolution and 70 microrad angular resolution will perfectly do the job to provide the separation that we need. Radiation tolerance, this we argued already. The levels of hadron fluence at the first vertex layer is 50 times larger than the Illumia HC. Conversely, the same levels of fluences are experienced at 27 centimeters. Okay, so you are 20. So, you know, with today you cannot build a CCHH detector unless you replace your vertex inner detectors every week or so. Okay, so this is one of the, I would say if you had to ask me what is the major showstopper to have a FCCHH detector today, would be this one. Okay, it's the levels of radiation. The rest we can do, but this we have to do some R&D to make detector which are harder, radiation harder than they are today. A lot of R&D is going on for doing for the LHC upgrade too. I hear that they can reach radiation levels of they can be radiation tolerant up to 10 to 17. So this is halfway there. So 20 years from now, probably doable, but today no. Hacking, okay, as a number of channels. The issue is for the innermost trackers, but for the innermost layer. But besides this, for the outer parts of the tracker with current technology, you can get there. This is actually, you can even get much better resolution than you get from the CMS phase 2 tracking systems. If you assume this resolution, this is the X2 mu invariant mass peak compared to the Illumia one, and you see you get at least a factor 2 improvement. And you get coverage up to 8/6, of course, with a much less good performance, but this gives you the ability to tag VBF jets, for example. One of the major challenges as well will be pileup, because if you think about you know, the average distance between vertices with a pileup 100, there will be a point when you go towards the forward region where the beam pipe alone, so when the track traverses the beam pipe, it will introduce a multiple scattering, which will introduce an uncertainty on the Z position of your track alone, which is larger than the separation between 2 pileup interactions. So beyond 2.5, regardless of whatever tracking system you put on top, you cannot resolve just from pure spatial reconstruction 2 pileup interactions, okay? Centrally you can do, but not above. So therefore you need to add another dimension to the reconstruction, and therefore, of course, you need the timing, which allows you to slice in times the beam crossing. And this can get you there. So if you get 25 picoseconds, you reduce the effective number of pileup interaction from 20 to 8. Of course, you would like to have an effective pileup interaction of 1. This means you can resolve every single interaction inside your bunch crossing. And if you assume 5 picoseconds, you get to 2, which is order 1. But 5 picoseconds is also something which we cannot really do today. Okay, so this doesn't mean you cannot do physics, right? But this is saying that. Of course, at eta 4, it's really a challenge. But of course, centrally, you can probably resolve this also without much aggressive timing resolution. Calorimetry, I won't discuss too much. I already told liquid argon calorimetry does the job, and scintillating tiles. There are also some full simulation studies with different level of pileup and pileup subtraction using only calorimeter information, using techniques of night reduction inside the clustering algorithms. And of course, these things will have an impact because one of the major physics case for FCCHH is measuring the XF coupling, for which you need very good diphoton invariant mass resolution, because you do this in the DIX channel, for example. Jet performance was also studied. You can see that this calorimeter with the pure software compensation can get you to 30% over square root T, which is not 20% over square root T, as discussed earlier, but still good enough. For the new ones, you have a standalone tracking resolution, as I told you, which is already 20% at 10 TV, but you would like 10% at 20 TV for the muons. It turns out that if you measure the angle of incidence of the muon track when it exits the calorimeter and enters the muon, it gives you an independent measurement of the muon momentum, of course, because it's related to it. And you can play the game with, with 1 or 2 muon stations. You can see how the standalone measurement. So this is interesting because this is the pure standalone muon momentum measurement from this angle. You see, this is the contribution of the multiple scattering of the muon within the calorimeter system, which is substantial because you have 11 interaction lengths before. But then if you combine with the tracking system, you see you can get there quite easily with these requirements here. And this is, okay, not something super challenging. Big challenge, of course, will be the data rates. I cannot go too much in detail now, but Atlas and CMS at level 1 will read out at 40 megahertz, of course, parts of the detector. This corresponds to 200 terabytes per second to read out. This seems feasible for FCCHH. The problem is that FCCHH will produce 10 times more data. So 1 petabyte per second seems hardly feasible also 30 years from now. So we'll need some kind of triggering system anyway. I mean, the dream initially would be, okay, let's read out everything, but probably it will be very hard and we need some kind of selectivity for doing things. But okay, there is time, and there is time also for new ideas. How we could probably improve this, highly speculative ideas. Probably more costly. Instead of liquid argon, we could use liquid xenon. Xenon is much more compact. It will give you much better resolution. You could use the one when these people are done doing physics, for example. Could be an option. Whether it's fast enough, I'm not sure, but I think it is. And you need, of course, 10 times picosecond resolution. You need a lot of stuff to happen before this gets there. But this would be one of the conditions to get to 1% to the self-coupling instead of 2-3. So improving the ECA resolution in an environment which is so radiation intense. Because again, we cannot use crystal, we cannot use all these calorimeters which give extremely good intrinsic resolution, which you have typically in a plus and minus environment. So you need to use something liquid. For maybe liquid xenon is an option, but okay. Maps, we heard this, but this gives you exquisite single point resolution, very low material budget, which is good for detecting, which is good for Higgs self-coupling. But the problem is that there are 3 orders of magnitudes away in terms of radiation hardness today. So you need a lot of developments for this to happen, but okay. Okay, this is just, how am I doing? At 11 with questions, but I started later. Because okay, if you want to hear some thoughts about the PV stuff, okay, let me just talk a bit about the physics. You probably are all familiar with this, but if we have a Higgs factor, it seems we will have a Higgs factory, I hope, before the Hadron Collider or the Muon Collider. So the Higgs factory is a Higgs factory. I don't like so much the term because a factory, you assume you produce many Higgses, but it's not true. A Higgs factory produces only 2 million Higgses in a very clean environment. But FCCHH or high-lumi LHC are more Higgs factories than high-lumi because they're dirty and they produce more. However, they are bad at doing hadronic final states. X2 glue, X2 BB, X2 CC, because the QCD backgrounds at the LHC are large. And this is why plus and minus collisions are good for doing this kind of things, where the decay rate is abundant, so the large branching ratios. Conversely, where the hadron colliders are good is for rare stuff because you produce many and they stick out with respect to QCD background. So X2 gamma gamma, X2 Z gamma, X2 mu mu, these kind of things. This is where you will really improve in a hadron collider. Of course, the Higgs self-coupling, because you can produce Higgs pairs. X2 invisible also, because branching ratio is 10 to the minus 4 in the standard model, and you want to probe a smaller value than that. Of course, hadron colliders are produce large number of Higgses, but you have the problem that if you want an absolute measurement, the production cross-section is typically poorly known because of PDFs, because of alpha strong uncertainties, because of missing higher orders, and calculations are more difficult. So typically what hadron colliders do very well is measure ratios where these things cancels. And if you have a plus and minus machine before, these ratios can become absolute measurements because you have measured these couplings very well at T plus and minus, okay? So this is a bit the synergy between the machines. Higgses, so 20 billion Higgses will be produced at the FCCHH. That's 100 times more than the DLHC. So this means a factor 10 in any statistical uncertainty. You take any Illumi measurement, you divide the statistics by a factor 10. Some of these measurements won't get you anywhere because, again, you are limited by the theory systematics. But for the rare measurements, you can put yourself in a place where you have so many Higgses that even at high PT, these things will be produced very abundantly. And there you are away from trigger thresholds, from things you don't understand experimentally very precisely. For example, you can do a ratio of x2 mu mu over x2 for mu. You have a lot of events even at 100, 200 GeV Higgs PT, and you can do a measurement at least with a statistical precision of below 1%. And if you can measure this below 1% at FCCE, then you have an absolute measurement of x2 mu mu coupling at few per mil. Okay, and this is very, very powerful. You can do the self-coupling. Of course, this is critically depending on the performance that you assume for your detector. For example, on your invariant mass resolution for the digest system, as you see, the different scenarios here for different center of mass energy, which I won't discuss too much here. I already discussed the impact on the photo resolution. But bottom line, it seems that if you combine all the channels, including also BB tau tau, we can get to 3% precision with FCCHH, which is at the level where statistics and systematics will be probably comparable, okay? Because theory also is not going to be easy for die Higgs below 1 or 2%. TT Higgs you can do fully differentially up to 1 TeV. This is good for doing interpretation and measuring the Yukawa in the IQ square regime. The bottom line is, as I promised earlier, you have all these abundant measurements that are below the percent for FCCE, for example, and then to go beyond the few percent regime to below percent, you need FCCHH, especially if you do it in combination with FCCE. Well, okay, this is I'm switching a little bit to BSM here. You know the role that all this model with an extra singlet play in the electroweak phase transition in the early universe. So it seems that at the FCCHH you can cover this small piece of space which was left out by Illumi HC. So this is something nice, and you can do it with just simply reinterpreting a singlet analysis of BB gamma gamma. You can do WIMPs. These are less motivated now because apparently the winners are excluded by indirect detection, but still you can reach xenos which are already which are still in the favorable range for the observed relic density. You can actually discover xeno above 1 TeV, which is where you would like it to be. I know winos as well up to and above 3 TeV, but the winos are apparently excluded. High mass resonances, okay, very trivially, you take the Illumi reach, you multiply by factor 7, and in some cases a bit less because of the problem of having to resolve the substructures of these objects, but you get pretty easily. Stops up to 10 TeV. And then I will just, as maybe a bridge to the final part of the talk, discuss a bit the various options that we have for 100 TeV, because I discussed earlier that our baseline now is this 84 TeV center of mass energy with 14 Tesla dipole magnets. Our accelerator friends have crafted a bunch of alternative scenarios for different magnet field strengths, from 12 to 17, 20, where 20 would be, the typical high temperature superconductors, different levels of luminosity. It turns out that very surprisingly, the 100 TeV is right in the right spot where synchrotron radiation power becomes a problem in PP collisions as well. So this is what we learn at school, that we can do PP because it's can reach high energy. Apparently 100 TeV is really where you start to have, you know, if you quantify it in terms of megawatt radiation per radiated per beam, which apparently our accelerator friends tell us this is kind of an upper limit to be able to cool the magnets efficiently and so on. Well, this is what you get at 17 TeV. At 17 Tesla magnets with 100 TeV collisions. So if you go to 120 TeV, then you have to limit the luminosity. You have to limit the current to be able to stay within those 5 megawatts. And so this also means that you know, if you look at the energy reaches for 100 TeV collisions, unless your analysis is very statistically limited, you won't gain much because you have to divide your integrated luminosity by a factor 3. Okay, so this is really one of the key results of this new study we did, is that at the end of the day, it doesn't really help, at least with the current knowledge, to go above 100 TeV. Also because magnets are more complicated. So with this in mind, how about we think about 1 PeV collisions? This was one of the requests from the organizers, and okay, I already apologized, but I will apologize again because none of this has to be written in stone. Maybe we have to remove the slides even after the talk. So I won't be held accountable for anything I'm saying here. But okay, let's do the exercise. So if you assume 20 Tesla magnets, then you would need a 500-kilometer ring, okay, to do a 1 PeV collider. You know, the problem is that for a fixed beam current, as I just discussed, the radiated power goes like the energy to the 4 over the radius. So if you want to keep your 5 megawatts per beam, you have to increase your radius by 10 to the 4. So this would give you a collider which is as big as the Earth, okay, for a 5 megawatt beam. So if you want to be able to cool down the magnets, or you produce 20 gigawatts of energy per beam, which is like maybe 20 power plants or something like this. So this is a bit difficult to cool down. So this is the scaling, and this is at least what I got by doing the exercise. So maybe there is some way out, but it seems to me it's not feasible to do a circular collider above, or at least with one order. It's not easy to scale an order of magnitude again up with the FCCHH. So the FCCHH will be probably the last hadron collider at multi-hundreds TeV energy or something. Yes, or you divide the luminosity by. You would need more, but even assuming the same, but you could reach this energy, but you can decrease the current by similar orders of magnitude. So, but okay, this we have to see what are the implications. It's not totally obvious to me that for pure discovery point of view, so if you have a Z prime of 500 TeV, maybe with 3 orders of magnitude less Lumi and the same lifetime, you might probably exclude it or see it, because the Z prime you exclude in the first week of the LHC, right? This is the first thing you do. You saturate very quickly the reach. So maybe this is an option. I don't know, but it's certainly is not an option for doing everything else in between. Okay. So probably, to go to this high energy, we need something different, probably something linear with very high gradients. If you do the exercise with 1 gigawatt per meter, which is what Wakefield promises, is you would need a 500 kilometer linear accelerator. Okay. This is not as big as the Earth, but it's probably then how you do the luminosity is another thing. But okay. Okay, so with this in mind, what will physics look like? So again, presumably a 1 PeV collider will be built to search for PeV resonances. So the central physics will be typically done with this typical 4 pi multipurpose detector. It will also search for, as I said, the rare physics processes for the same reason I discussed earlier. You can do things like a di-Higgs differential, for example, because you will have large rates, triple Higgs, things like this. This is the first thing that come in mind. 4 tops, whatever, all the di-Higgs production mechanisms, and whatever we will discover in between also, maybe, because maybe new physics is at 50 TeV, and this will be a machine that studies that new physics. So I don't know. So standard model physics will be continued to be measured, but will be produced even more forward. So at FCCH, the central spectrometer acceptance is limited by, I said before, by the beam pipe and the vertex placement at eta 4. So we need a forward spectrometer and solenoids, as argued. Here, every order of magnitude in energy buys you, well, not buys you, makes you pay 2 units in rapidity. So a Higgs at the LHC is produced with a Bjorken X of 10 to the minus 2, at the FCCHH with 10 to the minus 3, and at 1 PV collider with the Bjorken X of 10 to the minus 4. So probably you need PDFs anyway, so you probably need something like LHC or something, because I don't think PDFs are measured very precisely at those energy, but maybe they will argue otherwise. In terms of total imbalance, in terms of pseudo rapidity, you will produce Higgs up to eta equal 8. So you will have really, I think there it would make sense to have dedicated forward physics detector that do only Higgs top electroweak physics like we have for LHCb. I don't think LHCb will be still a thing, or at least a flavor factory, a flavor dedicated detector. These kind of detectors will also be able to do flavor, by the way. But if you do the math, the actual cross section increase from already from 10 to 100 TeV for B production is only a factor 5. So okay, maybe it makes sense to have a detector for that. I don't know. This is up to you to decide. But in terms of and from 100 to 1,000, it will only be another factor few. Will not be that much, right? So we need I think we will have, yeah, in this case, there will be like a dedicated forward physics detector and then something for central physics. I also played a bit. Yesterday I ran some cross-section leading, this is leading order, so these numbers probably can be multiplied by a factor of few, but it doesn't matter, just to see how things scale for the standard model processes. So as you might expect, stuff that increases the most is a high Q square process. Like for top, you get 60,000 more than we get at DHC. Triple Higgs, 5,000 more, etc. I mean, there's nothing fancy here, but I was curious to see how this thing scales. So the detector. Sorry, I switched this thing. I already discussed this a little bit, but again, if we go another order of magnitude larger in terms of energy, now we have the same requirements we'd have for 10 TeV tracks at 100 TeV. So a 100 TeV track to keep this 20% precision resolution, you need either 10 times better single point resolution. You look at maps give you 2-3 micron single point resolution. This is already the right ballpark. Now, of course, you would need to cover all your detector with maps. I don't know how many channels that will be. I don't know if it's radiation hard, but seems feasible. Magnetic field 10 times more, you forget it, because it will be a 20, 40 Tesla magnets, and then it would imply the loss of everything which is low momentum within the beam pipe and so on. A detector which is 3 times larger, because it scales like the square. I also doubt this will be the option that will be taken, because the detector cost scales like some power of this radius, right? Some powers between 2 and 3, because stuff that scales like surface is 2 and stuff that scales like volume is 3. Calorimeters typically scales like the volume because it's active material. Tracker is typically a number of layers, so you can think of, if you keep the same number of cylinders, then it would scale like the square. So if you have a 3 times larger detector, it costs 3 times more. Now a detector already at the level of 1 billion, you want 10 billion detectors. So it seems if you just do this, you increase the magnetic field by 4 to 5, you improve the single point by factor 3, and you increase the radius of the inner tracker by 1 to 1.5, you get a similar performance with CCHH. I mean, this seems okay. It doesn't seem completely out of this world in terms of tracking. It seems feasible, at least on paper. There are a bunch of things which I would like to see a bit more precisely. At some point, the nuclear interactions inside the tracker is not so opaque anymore as a function of the. This is the total PP in elastic cross section. These are numbers from the LHC, but this will tell you also how likely it is that the pion of a given energy interacts with the nucleus inside your detector, okay? And this is typically translates into inefficiency of tracking. It seems that if you increase by an order of magnitude, the energy, the cross section doesn't increase by orders of magnitude. It increases by a factor few. So if you have an inefficiency of 1% at 10 TeV, you will have an efficiency of 1.5% at 100 TeV. So it's not a big problem. A question I have is, at which energy these hadron nuclear interaction become more important than the Bremsstrahlung that that they will high energy tail of the DX. This is something one can play with Giant and understand, because these numbers, pi and nuclear interaction, is what physics was all about in the 60s. So probably these numbers are tabulated in somewhere. Calorimetry, again, I don't think it will be an issue, because the containment of the shower grows logarithmically with the energy. So you increase by factor 10 these, you just need a couple more interaction lengths to contain the shower. So a 100 TeV pion shower just needs a 20–30% thicker calorimeter. It's not dramatically different. You can also think about having heavier absorbers, and then you can keep the same size. Of course, tungsten, for example, costs more than lead, but okay. You can also think about putting the solenoids inside the calorimeter or within the ECAL and the HCAL, because solenoid is a big driver of the cost of the detector. The larger it is, of course, the more expensive it is. And so you might think about putting it earlier. For the muon, again, I think if anything, having more material before helps, because it's more, well, actually having more volume before helps, because it gives you a better measurement of the incident angle. This is just a by hand extrapolation of what it would require to have a 10% resolution at 100 TeV for a 100 TeV muon, which is what you would like to aim for. It doesn't seem anything too complicated. It requires a factor 3 improvement in single point resolution. You might argue that you might worry about a muon Bremsstrahlung inside the calorimeter, because you are in the tail of the DDX. This is where things will go south. But if you actually think carefully, the amount of energy loss is proportional to the energy. So in some sense, it's constant in relative terms. So 100 TeV muons, yes, will lose 20 GeV energy in the calorimeter, but you know, it's like a 10 TeV muon will lose 2 GeV energy. In terms of relative terms, is a fraction of it. I don't think it will affect momentum reconstruction. Okay, this is where things will be really bad. Boosted topologies, because we discussed earlier, it's already a big challenge for the FCCHH, but for 100 TeV W or Higgs, all the decay products are contained within an order of magnitude smaller. So this is like really well within the molar radius of a calorimeter, well within anything. So there is no way the calorimeter can give you any sort of information for identifying the stuff. It's also arguable that the tracking will be challenged by this kind of stuff, although typically tracking resolutions will be factor 5, 10-ish smaller than this. So probably you can get there. A W really looks like a tau. A Higgs look like the pi zero. Yeah, as I already said. This said, I mean, yeah, you can still resolve the pi zero at the end. I mean, you can still see the tracks of the, well, pi zero is not really correct, because you see the, if Higgs decays to dijet, you see the tracks within the detector. 50 TeV Bs, D, and taus, that's 5-meter lifetime. Now the B is completely decays outside your detector. So B behaves like a K long or a charge hadron, like a pion. For the Ds and taus, you have some of them will decay inside, and I think they will look like you know, like the pictures of omega minus we see in the textbooks. Like you know, K shorts or sigmas and things like this. But I mean, if you think about it, it's actually more complex than this, because these objects are very boosted. It would more decay like, again, something like this with, you know, a track jet, very collimated track jet within the detector. This looks really like a nuclear interaction if you think about it. So I don't know how we'll identify these things, honestly, or like a kink track or whatever. I mean, we have to do some. We will have to, or you know, next generation will have to do some thinking how to identify these things. Something nice, I think, is okay. This was already a discussion that people were having for the 100 TeV, but I think would become really relevant at PV energies, the weak showers. At the multi-hundreds of TeVs, the electroweak showers become important. Quarks radiate Ws, Z, and Higgses quite frequently. For example, a quark branches off to a quark W can become a problem for top identification, because the top is a W and a B. However, yeah, well, not however, actually, that will make it worse, because it will enrich the lepton content inside jets, because you produce Ws and Z, you will have more leptons, and then means that all the jets look more like Bs. So it will be a problem for B identification, I think. However, okay, these leptons won't be displaced, or at least won't be as much displaced as for a 5 TeV, because then the lepton is very, very, very displaced. On the bright side of things, neutrinos will shower a lot. And so this means that the neutrinos become visible, and so you can tell their direction more easily. If this will help for kinematic reconstruction, I think. And photons will convert in the vacuum to stuff like, you know, W plus, W minus. And so, I mean, yeah, I don't know what this implies for photon reconstruction, but we have to think a bit about these things. Okay, so, well, this is, I hope I didn't speak too much. Just to summarize, high energy proton collision are very inclusive facilities for doing physics. They can probe many different initial and final states, both for electroweak and colored particle. They can make measurements at thresholds and beyond thanks to the large rate and the high mass exploration. Actually, I had some new results on the high Q-square processes, standard model processes, but I didn't show them. The key physics benchmark channels which I discussed are setting the requirements for detector design, the physics reach for setting R&D goals, as was discussed in the previous talk, for optimizing the machine layout, of course, for software reconstruction. FCCHH is an order of magnitude more complex than the Illumina HC. Main challenges for me will be radiation hardness, amount of data, and timing. It will be the next generation hadron machine, probably, as we discussed the last, who knows? So it means that Illumina is a test ground for FCCHH, for also testing not only technologies, but new reconstruction techniques, like all this 5-dimensional reconstruction using timing information. So if anything, the Illumina will be useful for that. And it's synergetic with other proposed facilities. And then, okay, PV collisions will present yet another order of magnitude of new challenge, but of course, new opportunities.
Thank you. Okay, we definitely have to be done with coffee break before 11:30, the rule, but we can maybe do a few minutes of questions and then head over there. So good.
Oh, there is no estimate at all, because it will all depend on the assumed luminosity. I mean, if you assume the same luminosity as FCCHH, it will be the same level, because again, that's determined by the total proton-proton inelastic cross-section, which produces typically, you know, every order of magnitude will give you a factor 2 large. So yeah, you will have to improve radiation levels by factor 2 compared to FCCHH. It's not that big. What will kill you is if you increase the luminosity by another factor 10. But it already kills us at FCCHH. So, I mean, kills us. I mean, it's already the biggest challenge at FCCHH.
I'm curious for the pileup, to what extent is it more versus different? You know, how many of those 1,000 simultaneous events have higher energy than a Higgs processor?
No, it's a good question. It's a bit what I was trying to argue. It is more than different. It's actually almost the same, because at the end of the day, I think I have a table. I think somewhere I have. So if you look at the number of charge track per collisions, you see it's kind of the same, right? Typical proton-proton collision. This is not per bunch crossing. But then what determines the rate of total rate is because of more luminosity. But a typical collision looks kind of the same. It's 130 tracks versus 95.
For example, to put and right now we always assume that the vertex we care about, pretty much always, you know, our default assumption is the highest PT vertex,
Yeah.
right? Would that, if you're looking for Higgs physics, CCHH,
I would have to do the exercise, but yes, but to the extent that you can resolve every single vertex. I mean, you're trying to design a detector that now Illumina is aiming at reconstructing a large fraction of the 200 simultaneous collision that you have, and this allows you to not cut away Higgs. Here, your challenge will be to reconstruct all the 1,000 collisions at the same time. This requires 5 times better resolution in timing or in space, because that's basically the name of the game. But once you're done, because as I said, each collision looks the same as they look, more or less the same as what it looks at the Illumi.
Thanks very much. I like this very much. It's important and also fun to consider these things. In the first part of your talk, you talked about the trade-offs between different energies and luminosities and so on. It's a very important thing to do and not to be locked in on some number we name well in advance for the FCCHH. One thing to keep in mind is that in scaling from the LHC luminosity is in a sense artificially high because the benefit of having the LEP tunnel also restricted the energy that you could plausibly reach in the LHC. So it may be that we want to scale from that number, but it also may be that we could back off a little bit from it and reduce the requirements at 100 TeV. That has to be informed to some degree by the physics that we think might be there.
Yeah, this is a bit what we try to do in these scenarios here. Where you see, at the end you have the possibility. For example, if you were to decrease exactly what you're saying, if you were to decrease the energy for a 100-kilometer tunnel, this would buy you a lot of luminosity.
Exactly.
So
and,
at the point where you can even reach 3,000 pileups.
Right. So
then, okay, maybe you can build that kind of detector, and arguably, for most of the physics, unless your new physics is exactly, between 72 and 84 TeV.
Exactly.
Arguably, for precision physics, this scenario, if you can cope with that, will be better because you have a factor 2 Rumi, so you have.
Very good. So it's important not to be
Sure.
For men who are something locked into numbers. I'm told that when Carlo was first contemplating the LHC, he decreed that the energy would be 17.2 TeV.
Voilà.
And Emilio Picasso pointed out to him that if you want to do experiments and accelerate beams, you actually need straight sections. And we know we have straight sections in that. The other amusing remark is, for the last part of your talk, in 1982, Bjorkane gave summer school lectures called 1,000 TeV in the center of mass. We knew nothing, but this was before the Tevatron had operated, so there was no large-scale superconducting accelerator. Anyway, it's still fun to look back and see a very clever person trying to imagine, on the basis of very little experience, what we might be able to do to get to 1,000.
I did not have time to do some bibliography before, but I will definitely do later. Yes.
Okay, I think that we have to coffee in order to make our schedule, but we can do on this in the discussion section. Thank you for being willing to speculate for us.
Thanks.